Thank you everyone for joining us today. First, I'll deal with that rather cumbersome acronym. FREEDOM refers to a previous project funded under the NERC Environmental Risks to Infrastructure Innovation Programme. That project involved exploring with the water industry a wide range of factors driving change in dissolved organic matter in the upland drinking water supply. The current project involves a similar partnership, but of course has a more specific focus on building resilience to threats to the supply posed by climate change, hence the BCCR suffix. The project outcomes I'm presenting today result from the hard work and close cooperation of a wide range of scientific researchers and water industry representatives. We've had great support from our colleagues in Scottish Water, Yorkshire Water, Welsh Water, United Utilities and Irish Water. And if nothing else, in my opinion at least, we've developed an excellent working partnership that I hope will be sustained well beyond the current project. The UK uplands are a major and crucial component of the UK's total drinking water supply. And since this water source represents some of the least disturbed areas of the UK, you might imagine that the water it produces is relatively pure and not requiring of much treatment. But there's a complication in that the soils in these upland catchments, including peats, tend to be rich in organic matter. And as precipitation drains through them, some of the organic matter dissolves into the runoff, resulting in a brown staining of our upland stream and lake water. So the water reaching water treatment works in upland regions is often loaded with this dissolved organic matter. And this can create problems not only aesthetically with respect to taste and odour, but also because dissolved organic matter can react with chlorine during the disinfection process to create potentially carcinogenic disinfection byproducts. The water industry therefore has to reduce dissolved organic matter to low levels prior to this disinfection step by adding coagulants and through the use of other steps such as filtration. We define dissolved organic matter as all organic matter passing through a fine filter, for example a 0.45 micron filter. It's often quantified in terms of the concentration of dissolved organic carbon, and when organic carbon is measured in unfiltered samples, it's reported as total organic carbon. Traditionally, the water industry also uses various colorimetric approaches that report dissolved organic matter in terms of colour, measured in units of Hazens. And for upland waters, there's often a tight correlation between colour and dissolved organic carbon concentration. Dissolved organic matter comprises a whole spectrum of organic molecules derived from a wide range of sources. The current NERC multi-centre project LOCATE is investigating the production and fate of organic carbon throughout the terrestrial and aquatic system. And LOCATE modelers have reduced the complexity of the spectrum to 3 key functional types that they call T1, T2 and T3. In the case of our upland waters, the bulk of the composition comes from decaying plant material in soils, which produces both T1 and T2 types. Dissolved organic matter from more peaty sources tends to be dominated by humic substances, our T1 type. These are often large molecules possessing charged functional groups that influence the solubility of organic matter, its tendency to bind in the mineral soil, and tendency to be precipitated out by coagulants. Chromophores in these humic substances provide the colour while also making them vulnerable to degradation by ultraviolet radiation. T2 dissolved organic matter is also derived by soils but represents smaller molecules including proteins and carbohydrates that are less coloured, tend to pass more easily through the mineral soil, and are less susceptible to coagulants. Finally, our T3 type represents dissolved organic matter that's produced by aquatic life within the water itself, and particularly in lakes and reservoirs. This also tends to be relatively transparent and again doesn't respond much to coagulation. Ultimately, what's received in any particular water treatment works will represent a blend of these functional types, depending on the nature of the catchment soils, water residence time, trophic status of the reservoir and various other factors. Over recent decades, a major challenge has emerged for the water industry because dissolved organic matter concentrations have been increasing substantially, as demonstrated on the left here by dissolved organic carbon concentrations measured in a range of upland lakes on the UK Upland Waters Monitoring Network. Similar increases in dissolved organic matter have been identified in upland waters in many other parts of Northern Europe and North America, as indicated by the red and orange dots on the figure on the right. By analysing trends in these data sets, we've been able to establish that the long-term increase is mainly due to soil organic matter becoming more soluble as soils across these regions recover from the chronic effects of acid rain. As pollutant deposition is reaching very low levels now, any further response is likely to be small relative to change experienced over the last 30 years. But we also know that dissolved organic matter levels are sensitive to changes in the physical environment. The microbial activity that breaks down soil organic matter and makes it potentially soluble is known to be a temperature-dependent process. This is demonstrated in the plot on the left by Joe Clark's comparison of soil solution dissolved organic carbon concentration and temperature in a peat soil at the ECN site, Morehouse. The majority of source waters the industry has provided this project data for show this very characteristic sinusoidal cycle in the plot on the right, which we've been able to show largely reflects a damped soil temperature signal. The intensity, duration and timing of rainfall events can also be very important. In peat-dominated catchments, the dominant effect of rainfall is to dilute the organic matter. But things become more complicated when mineral soil is present. In this case, a significant proportion of our T1 DOC can sorb to soil surfaces when precipitation is only light and water is able to percolate vertically into the soil. However, if the soil becomes saturated by heavy rain, the switch in flow path and bypassing of the sticky mineral soil can result in heightened dissolved organic matter concentrations in runoff. And climate can also influence the production and processing of dissolved organic matter within reservoirs through changes in rates of water throughput, changes in water temperature and thermal stratification, and changes in solar radiation. Most water treatment works were developed in a very different time, when dissolved organic matter concentrations were considerably lower than they are today. They were designed with a significant tolerance in mind by engineers aware that concentrations vary from day to day over seasons and between years. Here we have a hypothetical water source where dissolved organic carbon has been increasing, primarily in response to soil recovery from acidification. While such changes were never anticipated by the industry, the tolerance in the treatment system has meant that up until now, the rise in concentration can be dealt with by increasing the coagulant dose. This has a cost, but it's generally considered manageable. However, every treatment works has its limit, beyond which further stepping up of the coagulant dose will be insufficient to prevent concentrations exceeding a level at which disinfection byproduct production would become unacceptable. Beyond this point, more radical modifications to the system will be required. This could mean the introduction of new plant, potentially costing millions of pounds in the case of, say, a new ion exchange system. Alternatively, a water company might need to consider a more flexible use of neighbouring water sources, depending on environmental conditions, or they may even decide that a particular treatment works is no longer economically viable. Consequently, the extent to which climate change is going to impact on future upland drinking water quality is a pressing and growing issue for the industry. They need to understand the likely impact on dissolved organic matter levels in order to guide their mitigation and adaptation strategies. So we formulated the FREEDOM-BCCR project proposal with the main objectives of providing clearer understanding of risks posed by climate change to future dissolved organic matter levels in order to inform mitigation and adaptation strategies, to facilitate long-term two-way research industry dissemination of knowledge necessary to build resilience, to create key performance indicators to inform impact on industry resilience, and finally to support the development of a predictive tool to provide a central means of communicating climate change risk and uncertainty. The project has involved a number of interacting work packages, but the key elements are as follows. Element 1 has involved the statistical analysis of water quality data from industry partners as a function of interpolated climate data. Element 2 has involved the development of a clearer understanding of how climate change might affect dissolved organic matter dynamics within reservoirs. And our lake modeler has been developing the lake algae prediction model PROTECH to include some dissolved organic matter functionality. Our land surface modelers have generated downscaled UKCP 18 model runs for various climate parameters under the RCP 8.5 scenario. Then the downscaled model projections have enabled both statistical and process-based models to project dissolved organic matter concentrations into the future. Most crucially, element 5 has involved the community of researchers and water industry representatives meeting regularly, initially face-to-face and later online, to consider how the industry currently deals with dissolved organic matter related issues and to consider the various iterations of the modelling runs and their implications. Finally, element 6 has involved the various communication and outreach activities of the community, and I'll get back to that later. We use data provided by the water companies in two ways. First, with Scottish Water, we were fortunate to have access to a regional data set of total organic carbon measurements for around 30 source waters covering the period 2013 to 18. 1 kilometre gridded temperature, precipitation and soil moisture data were obtained from Chess, Gear and Joules respectively. We then ran a series of site-specific linear models in which TSE was regressed against various combinations of antecedent precipitation and soil moisture windows, having first fixed the temperature variable on the basis of the phase of its seasonal cycle. Second, we obtained additional high temperature resolution dissolved organic carbon or colour data for selected sites from other water companies. As we had a broader set of chemical variables available for these sites, we were able to explore the data in more detail, and this included consideration of potential interactions between future climate change and further recovery from acidification. This table represents the best of 5 model fits for each of the Scottish Water source waters. The numbers represent the number of antecedent days over which the metric was averaged, while the colours indicate whether the effect was positive in red or negative in blue. The best fitting models, with variance explained mostly between around 50 to 70%, were for sites with greater peat coverage in their catchments. In most models, most of the variance was picked up by the temperature and rainfall variables, and soil moisture, while mopping up a bit of extra variance, had relatively little effect. You'll see that the effect of temperature is almost universally positive, while precipitation effects are mostly negative, mostly with windows covering several months. And the latter suggests that the dominant influence of rainfall on these systems is one of dilution. We're in the process of rerunning these models, substituting soil moisture for a second precipitation variable, as we suspect that this might show that there's a secondary positive influence of precipitation that operates over a shorter timescale at these sites. The PROTECH model has been developed specifically to capture how algae in lakes respond to changes in climate and nutrients. In the current project, Alex Elliott has been developing a DOC element to the model using coefficients representing temperature and radiation influences on the T1 to T3 fractions, as I referred to earlier. Future climate projections for our source waters were obtained from 12-kilometre regional climate model projections downscaled to 1 kilometre. And the CHESS methodology was applied to the 12-kilometre data to correct for topography, radiation, rainfall, and wind. A total of 4 ensemble runs was generated, including one representing the most warming and one representing the least warming, and 2 ensembles with a median warming rate, one of which had the largest decrease in summer precipitation. We're still in the process of finalizing our modeling work, but the key observations arising so far from the statistical modeling are that we've established a very clear relationship between temperature and dissolved organic matter concentrations. The plot on the right here represents an effective temperature response, or a Q10, as plotted against the extent of peat and peaty clay soil in the catchment. So this demonstrates that sites that have the highest proportions of peat or peaty clay tend to be the most sensitive to temperature. And we've also found that the sites with shorter residence times tend to be more sensitive than those with longer residence times. We have found that rainfall for these more peaty systems tends to be negatively correlated, so that the more rainfall, the greater the dilution. But in the less peaty sites, those more dominated by organomineral soils, can show the opposite response, where high rainfall leads to higher concentrations, particularly in the summer and autumn. The key observations from the PROTECH modelling are that reservoirs that aren't subject to substantial nutrient inputs from their catchments and tend to have little in the way of algae problems, in those sites, warmer water should increase the breakdown of dissolved organic matter within the lake basin. For those more eutrophied waters, the lakes will still act as a net sink, but the overall effect on dissolved organic matter will be smaller because of the effect of enhanced algal production and the generation of algal exudates. And so overall, the take-home message from this work is that measures to reduce nutrient loads to reservoirs will enhance the reservoir's ability to be a DOC sink. Here we have a couple of examples of the statistical modeling work. So here we have a model output in orange, plotted against the measured total organic carbon. So the model is essentially based on the combination of antecedent temperature, rainfall, and soil moisture. And you can see that it does a pretty good job in picking up interannual variation in total organic carbon, and particularly with respect to the peak heights and the trough heights as well. And for this particular site, the greatest influence on this interannual variation is due to variation in antecedent air temperature. We've then taken that model and used our UKCP 18 projections to project total organic carbon forward into the 2080s. So this model on the plot on the right provides model output on a monthly basis for 5 20-year periods. So we've essentially just come to the end of the green period, and the plot demonstrates that as time progresses, we see a gradual increase in total organic carbon in all months, but the changes are most marked in the summer months, and in this site the peak time is in September, October. Precipitation was more important at this site and appears to explain the relatively high TOC minima that we recorded in the winter of 2017. So this can be related to relatively low rainfall in the months leading up to that winter. Again, on the right, we've got the future projections, again with TOC peaking in the latter months of the year, and again the most marked effects are seen in those peak months of the year. So initial tentative findings from our modelling work suggest a wide range of responses to increasing temperatures and reductions in summer precipitation, with a heavy dependency on soil type and water residence time. The most notable increases are likely to be in more peat-dominated catchments with short residence times. So we've tried to capture this differential behaviour in this table here. These results and classifications are likely to change as we develop the modelling work further. In the process of our early meetings, it became clear to us that the resilience of the drinking water system to what might be quite widespread increases in dissolved organic matter can be considered in terms of a chain of potential intervention options. So during the summer that has just gone, we held a series of seminars to consider 3 main areas of potential intervention. In the first instance, there's a need to consider whether there's anything that can be done at source. And we've been combing the scientific literature to try and establish whether there's any scientific consensus for any of the management measures listed on this slide having a significant influence on dissolved organic matter concentrations. There's clearly been a huge investment by water companies and others in peatland restoration. And much of this has involved the blocking of drains and the encouragement of re-wetting and re-establishment of peat-forming moss species. And there are plenty of good news stories emerging from this surrounding the impact of the intervention on biodiversity and peat-forming moss species and improved carbon sequestration. But it seems the jury is still out as to whether such actions have a significant effect in reducing dissolved organic matter concentrations, at least at a catchment scale. More generally, our literature search found that there was quite a lot of evidence linking forestry to changes in dissolved organic matter, particularly when it came to disturbance caused by planting and felling in peaty areas, which can lead to at least short, if not medium-term, increases in dissolved organic matter concentrations. With respect to interventions within reservoirs themselves, it was recognized that in some stratifying lakes, dissolved organic matter concentrations could vary significantly with depth, depending on the dominant source and the sink strength of the reservoir. And we concluded that it would be worth considering whether more within reservoir monitoring of temperature and water quality profiles might help to enable a strategy of varying the height of draw-off of water depending on the conditions in the reservoirs at the time. And finally, we considered the adaptation and mitigation options open to the industry at water treatment works themselves. As I explained earlier, the obvious response to rising concentrations is often to increase the dosing of coagulants, but these have their limits, and so it will increasingly be important to consider other options. One area that we've identified that really is worth further investigation is with respect to the extent to which we can monitor not only concentrations of dissolved organic matter, but the chemical quality of that organic matter, as the quality has a big impact on the types of treatment that may be effective in removing it. So real-time monitoring, not only of concentrations, but of dissolved organic matter quality, appears to be a really important area for development. Ultimately, again, as I explained earlier on, the only option may be for the installation of new plant, such as a magnetic ion exchange system, but these measures can be extremely expensive. So the project's ended up with this conceptual view of the resilience issue. In this plot, on the horizontal axis, we have the likely extent of the effect of climate change on dissolved organic matter concentrations and treatability. And on the vertical axis, we have the stability of the water supply in relation to the infrastructure currently in place. Providing climate change impacts on a particular water source are not considered to be that significant, and the current infrastructure is considered adequate for the current envelope of variability, our site is likely to sit here at the bottom left of the diagram, covered by the current capacity of the system and normal operating expenses, as referred to as OPEX. If we're forecasting more significant dissolved organic matter increases in sources that are approaching operational capacity, the site might sit here in the middle of the diagram and will most likely require further operational expenditure on coagulants, for example, in addition to other measures that can be taken, for example, within catchments or reservoirs. And if our projections are that concentrations are going to exceed current capacity, the current resilience of the system will have been overwhelmed, and a substantial capital expenditure, or CapEx, may be necessary before we can ensure future resilience. So, as I hope I've demonstrated in this presentation, the project has made considerable steps forward in terms of understanding the current influence of climate on variability of dissolved organic matter in upland drinking water sources, and we've tried to provide the water industry with our best estimates of the direction of travel by linking our model output with our climate projections. And we have had a superb amount of exchange of information and ideas at our numerous workshops. So we're now at the stage where we're writing a lot of this work up in form of reports, but we're also trying to produce various other forms of communication. For example, on the right here, we have the first of a number of briefing notes that we're producing for the industry. In addition to that, we will be hopefully writing up this work. We have an opinion piece planned, and there should be a number of other peer-reviewed publications in the pipeline describing the outcomes of the modelling approaches. summarize, I believe the project has mostly achieved what it set out to do. We've developed a great community with our industry colleagues, and our exchanges have been a huge learning opportunity for the researchers at least, and I hope the feeling is reciprocated. The projects involve the free sharing of ideas and data and has resulted in a clearer understanding of the likely scale of the climate change problem and the options open to the industry to increase resilience. It's important to stress that there are elements of the predictive work which still need to be finalised, but it's clear that climate change does pose significant risks, particularly for smaller and more peat-dominated systems and their treatment works. And while modelling has been effective in capturing much of the behaviour in dissolved organic matter in these systems, a major outstanding area we've found is with respect to responses to extreme events, which are quite difficult to model using the techniques that we've used during this project. And we're thinking particularly of intense rainfall events, which are predicted to become more intense and more frequent in future. We believe that the community that we've developed would be well placed to explore these issues in future. So thank you very much for listening today. We would welcome any feedback.